Hello everyone, my name is Daniel Mudrov and I will be presenting on phosphoglycerate kinase. Here in figure 1, we have an image of phosphoglycerate kinase, or PGK, which is the enzyme in the 7th step of glycolysis. It catalyzes one of the ATP generating reactions in glycolysis to produce a single molecule of ATP. It is typically found as a monomeric enzyme, meaning that it is formed from a single polypeptide chain, such as the PGK of the bacterium Thermotoga maritima, which will be analyzed here. The enzyme is composed of alpha helices, beta sheets, and random coils. The structure of phosphoglycerate kinase, named 1-VBE, from Thermotoga maritima was solved by X-ray crystallography using X-ray diffraction. The crystal structure obtained from the Protein Data Bank website does not contain any artifacts stemming from the crystallography process. There are 3 ligands present in the enzyme crystal structure: phosphoaminophosphonic acid adenylate ester, or ANP, which is an ATP analog, 3-phosphoglyceric acid, or 3-PG, which is simply the protonated form of 3-phosphoglycerate, and a magnesium ion. ANP is a non-hydrolyzable ATP analog that may have been used instead of ATP by the researchers to prevent hydrolysis, so that the interactions between the enzyme and the non-hydrolyzed ATP analog can be investigated in detail. Here we see 3-PG colored in cyan carbons, magnesium ion colored in chartreuse green, and ANP colored in yellow carbons. Here are the ligands and key residues involved, and these are presented in their ionization state at physiological pH of around 7.4, which can be seen in figure 2. PGK performs the mechanism by reacting ADP with 1,3-biphosphoglycerate to produce 3-phosphoglycerate and ATP. The reaction is catalyzed in the presence of a free magnesium ion, which is a required cofactor. ADP carries a -3 charge, 1,3-biphosphoglycerate carries a -4 charge, ATP carries a -4 charge, 3-phosphoglycerate carries a -3 charge, magnesium carries its natural +2 charge, and for the key residues, arginine 36 carries a +1 charge, glycine 354 is neutral, and lysine 197 carries a +1 charge. Here in figure 3, we can see the active site's polar contacts. So shown are the ligands surrounded by the active site residues that are all within a 5 angstrom distance. The amino acids close enough to contact the ligands are arginine 151, arginine 62, arginine 118, histidine 59, aspartic acid 21, asparagine 23, arginine 36, lysine 197, glycine 354, serine 356, aspartic acid 355, glutamic acid 324, glycine 293, alanine 196, asparagine 317, and lysine 201. The interactions are shown in dotted yellow lines, and the distances are displayed in angstroms. There are numerous interactions occurring between the ligands and active site residues, including salt bridges, hydrogen bonding, and water-mediated polar contacts occurring through the side chains of the active site residues. It appears that these interactions are key to binding between the active site residues and the ligands. The key residues are color-coded in green. The rest of the active site residues are colored in magenta, and the water molecules are colored in red. Figure 4 Figure 4 here shows the interactions with 3PG, and the active site residues that interact with 3PG are lysine 197, arginine 151, arginine 62, arginine 118, histidine 59, asparagine 23, aspartic acid 21, and arginine 36. So we can see hydrogen bonding occurring through arginine 36 and the double bonded oxygen of 3PG. In addition, 3PG has water-mediated contacts with lysine 197, seen here, arginine 151, seen here, arginine 118, here, and asparagine 23, here. Figure 5 shows the interactions with ANP, and the active site residues that interact with ANP are glycine 354, serine 356, aspartic acid 355, glutamic acid 324, glycine 293, alanine 196, lysine 197, lysine 201, and asparagine 317. We can see a salt bridge interaction, a salt bridge between lysine 201 and the ANP gamma phosphate oxygen. Furthermore, we can see water-mediated contacts occurring through glutamic acid 324 and the hydroxyl groups of the ribose sugar in ANP, seen here. ANP also has interactions mediated through the backbones of glycine 354, aspartic acid 355, serine 356, glycine 293, alanine 196, and lysine 197. We should note that lysine 197 interacts with both ligands. It interacts with 3PG through its side chain and ANP through its backbone. Let's go over the reaction mechanism. So in figure 6, we can see the reaction mechanism, and the mechanism is composed of an SN2 reaction. PGK removes an inorganic phosphate from the 1' carbon of 1,3-biphosphoglycerate to form 3-phosphoglycerate, and then it transfers the inorganic phosphate from 1,3-biphosphoglycerate to ADP to form a molecule of ATP. When the enzyme conforms to its closed conformation, it positions ADP in close vicinity to 1,3-biphosphoglycerate. Subsequently, the ADP beta phosphate oxygen performs a nucleophilic attack on the 1-phosphate group of 1,3-biphosphoglycerate. This leads to the formation of a charged transition state, which is stabilized by lysine 197 and glycine 354. The inorganic phosphate is transferred in a single displacement mechanism, with lysine 197 acting as a phosphoryl gripper that guides the inorganic phosphate from 1,3-biphosphoglycerate to ADP. Arginine 36 is bound to a water molecule that is centered in the trajectory of the inorganic phosphate transfer, and its guanidinium group interacts with the carboxylate group of 3-phosphoglycerate after catalysis. The magnesium ion coordinates with the non-bridging oxygens in ADP, and then the non-bridging oxygens of ATP to stabilize the molecules. Here in figure 7, we will look at the residues that are involved in changing the enzyme's conformation from open to closed. So for the enzyme to conform to its closed conformation, there's a series of salt bridge disruptions and formations of new salt bridges. The residues involved are glutamic acid 186, lysine 180, leucine 178, threonine 374, glycine 375, glycine 376, glycine 377, arginine 62, arginine 36, and aspartic acid 200. The residues that are involved in this are colored in magenta. Initially, there is a bending of the helix between leucine 178 and lysine 180, causing the salt bridge between lysine 180 and glutamic acid 186 to break, and this unlocks the open conformation of the enzyme. Subsequently, threonine 374 moves towards arginine 36, and this reorients the residues glycine 375 through glycine 377. The closed conformation is then secured by the establishment of a salt bridge between arginine 62 and aspartic acid 200. Here in figure 8 is an image showing the surface view of the binding pocket. The enzyme conforms to the closed conformation once both substrates ADP and 1,3-biphosphoglycerates are bound to the active sites. It can be observed that the active site is mainly occluded within the enzyme, causing the ligands to be tucked away inside of the binding pocket. A reason for this is to protect the ATP molecule from hydrolysis. Here in figure 9 are the hydrophobic interactions that occur between the ligands and hydrophobic residues. It can be seen that ANP has much more hydrophobic interactions compared to 3PG. The hydrophobic residues are colored in magenta, while the hydrophobic contacts are colored in green cyan. Figure 10 shows the hydrophobic interaction of 3PG. So 3PG only has one apparent hydrophobic interaction occurring with glycine 147. The interaction occurs between the glycine 147 residue and the carbon backbone of 3PG. Here in figure 11, we can see the hydrophobic interactions of A and P. ANP has a plethora of hydrophobic interactions around its adenine, ribose sugar, and phosphate tail. Furthermore, the hydrophobic interactions in ANP occur between nonpolar and polar atoms. We can see glycine 376 and glycine 377 interacting with the polar ANP gamma phosphate oxygens. This may be attributed to several reasons, including that ANP is enclosed by much more hydrophobic residues, and the enzyme conforms to a closed conformation, shielding it from water molecules to prevent hydrolysis. These factors could contribute to reduced polarity, resulting in hydrophobic interactions to transiently occur with polar atoms. Also, so this is ANP, and we can see that between the beta phosphate and gamma phosphate, there's a nitrogen, which makes this molecule non-hydrolyzable. If this were an ATP molecule, the beta phosphate and gamma phosphate would be connected by a bridging oxygen, which would make it susceptible to hydrolysis. Here, figure 12 shows the enzyme surface shown in mesh format. And this highlights the hydrophobicity of the binding pocket. So once again, the hydrophobic residues are colored in magenta. So the PGK enzyme conforms to a closed conformation that intends to maximize shielding from water particles during the reaction, so that the newly formed ATP molecule will not be hydrolyzed. This is reinforced by the fact that both 3PG and ANP are occluded within the binding pocket and are enclosed by a lot of hydrophobic residues, especially, which is the case for ANP. Actually, in fact, ANP is surrounded by many more hydrophobic residues than 3PG. Here are my references, and this is the end of my presentation. Thank you for watching.